I can build a new one, which I'll call the external direct sum. It's often written with these plus signs and circles. So the underlying set is the Cartesian product, and it's the obvious addition you add in each factor and scalar multiplication. Basically, you would probably want to call this a direct product, but it's usually called a direct sum. If you call it a direct product, that's fine too, actually. So for instance, c to the n is nothing more than a direct sum of n copies of c. Okay, well, we can combine this with representations. So now let's suppose I have a bunch of representations, I'll call them phi upper k in parentheses, of the same group into different vector spaces. K runs from, say, 1 up to n. Then there's a corresponding external direct sum, or just direct sum, representation phi, which goes from G to the general linear group of the direct sum vector space. And it's defined by the obvious formula. Phi sub G, for an element of the group, of an element in the direct sum vector space, which is a tuple of vectors, you just apply each of the original representations in each factor. It's the only formula that really even makes sense. And then you can check that's a representation. And the notation for this new representation, it's a little bit of an abusive notation. We'll write the direct sum of the maps. So that's notation for this direct sum representation. So for instance, we can do this for matrix representations. So let's just do it with two factors. Maybe the two vector spaces are standard vector spaces. Then, in this case, the direct sum vector space you can identify with another standard vector space. So now if I have two different representations, let's call them phi j, going from G to GL n sub JC, J is either 1 or 2, then I can produce a new representation, which will be the direct sum representation. And because of this identification, that's going to go to GL n sub 1 plus n sub 2 of C. And if you write it out, what you get is a block matrix decomposition. So I'll put the matrix phi upper 1 G here, and the matrix phi upper 2 G here, and 0 here. These are blocks, because the original things are matrices. I think that's pretty straightforward to think about, and so it's easy to construct new representations by forming a direct sum. There's also a notion of an internal direct sum of a vector space V, which has some subspaces, let's call them V1 up to Vn. And it's an internal direct sum if the obvious function from the external direct sum to the original vector space is an isomorphism. The obvious function is the one that takes the elements in the various subspaces and adds them up. For instance, if n equals 2, this means that these two subspaces have trivial intersection and span the whole space. When n is greater than 2, there's a more complicated condition, but you can probably figure out what it is because we've done very similar things for groups. So of course, because of this, we can also talk about an internal direct sum of representations. So if I have a representation to some vector space, and I have invariant subspaces, so they're not just subspaces, but they're invariant subspaces under the representation, such that V as a vector space is a direct sum of those subspaces, then I'll say that phi is an internal direct sum as a representation of the subrepresentations phi restricted to each of the VKs. This language is more or less straightforward. It's similar to the way we've talked about groups. As a consequence, the phi will be equivalent to the external direct sum of those subrepresentations. Now we have some definitions. A representation is said to be decomposable if it is a direct sum of two proper and non-trivial subrepresentations. In other words, we've got invariant subspaces which are both not the trivial subspace, but whose intersection is trivial and whose span is everything. Given that, of course, phi is equivalent to the direct sum of the restrictions, but the point is that the restrictions are not themselves trivial. So it's an interesting direct sum decomposition. If one of the factors is the zero space, it's not interesting. One more definition, the representation is said to be completely reducible if there exists an equivalence to a direct sum of a finite collection of representations such that each of these representations is irreducible. That is, each of the representations phi k has no proper non-trivial subrepresentations. It's going to turn out that all finite dimensional representations of finite groups are completely reducible. So we will analyze our representations by showing they're equivalent to a direct sum of irreducibles, and then we'll try to classify the irreducibles. That's going to be the plan.